In this problem, we're going to examine an exponential function. We're going to use the function f of x equals 4 to the x plus 1 minus 2 to find the domain of the function, graph the function, and from the graph determine the range and any asymptotes, then find the inverse of the function, use the inverse to find the range of the function, and then graph the inverse. Start by finding the domain of the function. We first recognize that the base function is y equals 4 to the x. This exponential function has a domain of all real numbers. If we examine the given function, see that there's a transformation of a shift left 1 unit, and there'll be a transformation of a shift down 2 units. Neither of those transformations will have an impact on our domain, so the domain for our function is still all real numbers, or in interval notation, negative infinity to infinity. We want to sketch the graph of our function. We'll go ahead and start with the base function. We'll plot a few points and then use transformations to get the graph of our given function. Our base function y equals 4 to the x has a horizontal asymptote at y equal to 0. And if we plot a couple of points, we'll let x equal 0. 4 to the 0 is 1. We'll get the point 0, 1. It's the graph of the base function. And then if we let x equal 1, we get y equals 4. So we plot the point 1 comma 4. We'll go ahead and plot one other point. If we let x equal 2, we'll get y equals 16. Again, this is for our base function, y equals 4 to the x. We connect these dots, connect the points with a smooth curve, and then approach our horizontal asymptote as we go to the left. We have the graph of our base function, y equals 4 to the x. Now, to get the graph of our given function, f of x, we're going to apply some transformations. We're going to go left 1 unit and down 2 units. So we'll use each of the 3 points that we've plotted on our base function and apply the transformations. So starting at the point 0, 1, we'll go left 1 unit, down 2 units, and we get the point negative 1, negative 1. Starting with the point 1, 4, we go left 1 unit, down 2 units. We get the point 0, 2. From 2, 16, we go left 1 unit, down 2 units. At the point 1 comma 14. We had a horizontal asymptote in our base function of y equals 0. If we apply our transformations, a shift left 1 unit does not affect the horizontal asymptote, but the shift down 2 units will give us a new horizontal asymptote, y equals negative 2. We'll go ahead and plot or connect the points that we've plotted here with a smooth curve. Again, as we go to the left, we'll approach our horizontal asymptote. And so we have the graph of f of x. Now, in part C, we were asked to, from the graph, determine the range and any asymptotes. From the graph for f of x, we can see that the range will be the set of values for y that are greater than negative 2. In interval notation, let's say the range is from negative 2 to infinity. We saw with our transformations that we get a new horizontal asymptote of y equal to negative 2. So we'll list that horizontal asymptote, y equal negative 2. Now that we have the graph of our exponential function, we're going to shift our attention to finding the inverse of the function. We were given the exponential function f of x equals 4 to the x plus 1 minus 2. To find the inverse, we'll start by writing y equals 4 to the x plus 1 minus 2. Then we'll interchange the variables. We get x is equal to 4 to the y plus 1 minus 2. This will implicitly define the inverse function. We now need to solve for y. First thing we're going to do is isolate our exponential portion by adding 2 to both sides. So we'll have x plus 2 equals 4 to the y plus 1. Now here we're going to change form. Right now we have the exponential form. We're going to change to the logarithmic form of the equation. This will be log base 4 of x plus 2 is equal to y plus 1. Now we're trying to isolate y, so we're going to subtract 1 from both sides. We'll get log base 4 of x plus 2, then minus 1 is equal to y. This will be our inverse function, f inverse of x. And we should verify that f of f inverse of x is equal to x, as well as f inverse of f of x is equal to x. But we'll leave that check to you. In part C of this problem, we use the graph of the function to determine the range of the function. In part E, we're going to use the inverse function to determine the range as well. We found that the inverse function, f inverse of x, was log base 4 of x plus 2 minus 1. Recall that our original function was the exponential function f of x equals 4 to the x plus 1 minus 2. We want to use the inverse function to determine the range of our function f. We'll do this by recalling that the domain of our inverse function is equivalent to the range of the function, and vice versa. The domain of our function is equal to the range of the inverse. So if we can find the domain of our inverse function, that will allow us to determine the range of our original function. Looking at this logarithmic expression, we see that the domain is a set of values such that x plus 2 is greater than 0, or x is greater than negative 2. So the domain of the inverse function is a set of values that are greater than negative 2. Therefore, we can say the range of f will be the set of values for y that are greater than negative 2. In interval notation, we'd say the range is from negative 2 to infinity in parentheses. The last part of this problem asks us to graph the inverse function. We could do this by plotting points, by using transformations, or by using the graph of the function f. We're going to do this by using the graph of the function f. So we'd like to obtain the graph of f inverse of x, which is log base 4 of x plus 2 minus 1. We graphed our function f of x, and we plotted 3 points, the point negative 1, negative 1, the point 0, 2, the point 1, 14, and we had a horizontal asymptote of y equal negative 2. The relationship between the inverse function and the function is that if the point AB is on the graph of f, then the point BA must be on the graph of the inverse. So we switch the coordinates of the points we plotted for f, and we'll get points that we can plot for the graph of our inverse. We'll start with negative 1, negative 1. If we switch the coordinates, we actually obtain the same point, negative 1, negative 1. Taking the point 0, 2 and switching the coordinates will give us the point 2, 0. Taking the point 1, 14 and switching the coordinates will give us the point 14, 12, 14. It's 14, 1. We had a horizontal asymptote of y equal to negative 2. We're basically switching the x's and y's, so to graph our inverse function, we'll end up with a vertical asymptote at x equal to negative 2. And if we were to connect the 3 points with a smooth curve and approach our vertical asymptote, we would have the graph of our inverse function, f inverse of x. And we've got both the function and the inverse on the same graph. We've also drawn the line y equal to x to show the symmetry between the graphs of the function and the graphs of the inverse and the function. The two graphs are symmetric around this line y equal to x. And that gives us our reflective property with our points.